widely known scientist in the world, very popular, even among three-wheeler driver. You ask, he will know Albert Einstein, at least heard about him. No other scientist so popular like Einstein. This young Einstein, middle-aged Einstein, retired Einstein. So he was a genius. He contributed a lot to modern science, modern technology. We are enjoying those things, whether it's electricity or transistor or mobile phone or computer or laser. It is because of his contribution that things have moved forward. This was Einstein, a violinist and a very popular figure in general public among students. Okay, this is Marie Curie, who discovered radioactivity, double Nobel Prize winner for radioactivity and for chemistry, who contributed a lot to the field of medicine, being a physicist. Richard Feynman, very recent times, a great physicist, again a Nobel Prize winner, and he was the one who told the world the potential of nanotechnology. He said nanotechnology, people can gain a lot of benefits in the future. Right, so physics helps us to understand the planetary motion, steam engines, radios, cars, television, microwaves, transistors, computers, lasers. Some of these are based on Newton's laws and we call classical or old physics. Some of these applications like computers, lasers are based on new physics, new theories, quantum mechanics, etc. To understand light, when you send a beam of sunlight through a prism, it gets scattered into various colors. So these are few examples. Properties of light, colors, reflection, mirrors, all these things are now being used in cameras, optical fibers for quick communication instead of copper wires, telescopes, microscopes, photo detectors and sensors. All these use the very basic principles of light. Another example, transistor, as I mentioned, was discovered in the 1960s by some Bell Labs researchers. His research team, Shockley, Breton and Bardeen. So the first very crude transistor, PN junction transistor, very crude one, very big. Maybe few transistor was something like this size. We have 3 terminals. Now the present day IC chip, you have many thousands of transistors inside this. So the size of the transistor, people have been able to decrease in size and put more transistors in a chip, which led to the development of computers and other integrated circuits. So we'll skip that. Okay, now I am slightly diverting this attention. So as I mentioned, physicists study very large things, stars, planets and galaxies. Also small things like molecules, atoms and electrons. So it's very important for a physicist or even a student who want to study physics to understand the size of things. The size, how many centimeters or meters, the distances. When we study galaxies, we have to use a very large length scale, much more than thousands of kilometers. So we use light year. 1 light year is the distance through which the light travels during 1 year. So it's a huge distance. So we measure light years to measure distances between galaxies. And we measure nanometers, for example, to measure atomic dimensions. So these, maybe some of you may know these things. So we use powers of 10. Speed of light is 3 into 10 to the 8 meters per second. 10 to the 8 means 1 and 8 zeros. Okay? So it's a very large one. So what is the distance that the light travels during 1 year? You can see it's a huge distance, 10 to the 16 meters. Light will travel 1 year. These are the distances used to measure the galaxies or astronomical ones. Then kilometers we use for day-to-day things. Okay, how many kilometers? The distance from here to Jaffna or whatever. 1 centimeter. So these are the things we use in ordinary day-to-day things. How many centimeters? What's your height? So many meters, centimeters. And as we go down, we use millimeters. We can see micrometers. We can hardly see, but we can see micrometers using an optical microscope. We go still down, nanometers. You need very powerful electron mics. Beyond that, we cannot see. Picometers and femtometers, we cannot see. They are very, very small. So we use light years to study galaxies, kilometers for the planets, maybe thousands of kilometers. Kilometers again on Earth distances. Meters and centimeters. Size of human beings, buildings, roads, vehicles. Meters and centimeters. We go still down, micrometers. For example, bacteria, red blood cells, they are micrometer size entities. We go still down, DNA molecules is few nanometers in width. We go still down, picometers are the atomic sizes. So the atom has protons and neutrons. Now physicists believe proton and neutron are not elementary particles, but consist of still smaller entities called quarks. Now we have experimental evidence for the proton and neutron and the electron. We have experimental evidences. But for quarks, there are indirect evidences. People have not seen them yet through any equipment. So quarks are believed to be building blocks of protons and neutrons, which are the building blocks of molecules and matter and planets and space. So the people believe quarks are the fundamental building blocks of nature. Is nature. Okay. So yeah, let's skip this. Yeah. Now there is a tiny video clip. It will take about 10 minutes. It's called Powers of 10. I will briefly mention what is there. This is a simulation. Okay, simulation. A family spent their weekend in a Chicago park in the USA. Husband and wife relaxing, you will see. And then something, camera-like thing will focus onto their place. This camera is taken out into air and then has large distances, large heights from Earth, then away from the Earth, goes further into astronomical distances, like a focusing of telescope. Okay? Then we come down from galaxies, you come down again to these human beings, then you go in to their, through the skin, to see micrometer things, nanometer things, molecules and atoms. Okay, it's a simulation, but I hope you will enjoy it. So after that we will take some questions.
The picnic near the lakeside in Chicago is the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Power boats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters, the distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity.